In 1995, the Hubble telescope gave us this incredible image of the Pillars of Creation, a structure within the broader Star Queen Nebula, also known as the Eagle Nebula. The image was done in the SHO palette, where the light emitted by sulfur ions is assigned the color red, the light emitted by hydrogen ions is assigned the color green, and the light emitted by oxygen is assigned the color blue. This image, while scientifically revealing for its clarity, became famous for its beauty, and the SHO palette also became known as the Hubble palette. The palette was very useful. In particular, it allowed scientists to look at an image and clearly distinguish between hydrogen and sulfur, which emit almost exactly the same color of light. They both emit visible light deep into the red side of the spectrum. To illustrate, in the image above, I have portrayed sulfur information with hydrogen information. Can you tell which is which? Let me divide them out for you. It is almost impossible for the human eye to tell one from the other by color. But what would happen were I to assign another color to the hydrogen part of the image? Following the model of the Hubble palette, I'll assign hydrogen to green and sulfur to red. Now, let's see what happens when I composite the two colors together. I'll use the light in composite mode, which will simply add all the information but respect the brighter regions so that bright areas added to bright areas will not blow them out. While one could not say that the image looks good at this point, at least not unless you're a scientist wanting to distinguish the materials within the image, in which case the information is now elegant and beautiful. But for aesthetic purposes as well as general study, there is at least better distinction of the different regions and materials within the region. Of course, this is only a very rough composite. All the information, such as the information within the nitrogen and oxygen spectrum, has not yet been added to the image. Nor has the information been luminance balanced nor sharpened. If it were, it would look like the NASA image, like this. Now the Hubble telescope shoots at a lot greater magnification, 57.6 meters of focal length to be precise, while the information that I've used to create this video I've derived from my own telescope, which shoots anywhere from a mere 0.4 meters to just over 2 meters of focal length, and presently I have it set for 1.28 meters of focal length. So, for an apples-to-apples comparison, we had to zoom in and just reveal the central structure known as the Pillars of Creation, shown here. And what we are presently seeing is the Hubble telescope's SHO version of the Pillars of Creation within the Eagle or Star Queen Nebula, where sulfur has been assigned to red, hydrogen has been assigned to green, and oxygen has been assigned to blue. Since hydrogen and sulfur emit such similar wavelengths of light, and it's very difficult to discern one from another by natural color, this false color method creates clarity within the image. The information is derived by passing the light coming from the Eagle Nebula through various filters. One filter allows specifically the frequency of light emitted by hydrogen ions to pass through it. Another filter allows specifically the light emitted by sulfur ions to pass through it, and the other filter allows specifically the light emitted by oxygen ions to pass through it. Color is assigned to each frequency to create clarity within the image as we see here, and it has the side effect of being very beautiful. That's beyond doubt. When applied to nebulous structures, the SHO palette is gorgeous. When NASA released this image to the general public, it was spectacularly received, portraying not only the power of the Hubble telescope and humankind's ability to observe the cosmos, but also heralding the sublime beauty that can be found all throughout the cosmos. Nearly 2 decades later, NASA pointed the James Webb Orbital Telescope at the Pillars of Creation and took this image. It was shot in the infrared spectrum. Infrared light is capable of passing through a great deal of dust and gas, effectively allowing the portrayal of much of what is going on within the Pillars of Creation. Now, the infrared frequencies that the JWST operates in is a range of light invisible to the human eye. So, while this image might resemble the famous SHO Hubble palette, it's not actually assigning sulfur to red and hydrogen to green like the Hubble palette does. Rather, it assigns colors to frequencies to best reveal the inner structure of the pillars. And the ability of the JWST to reveal inner structure like this makes this image immensely scientifically valuable. It's also very beautiful, and it too went viral. But such images do not relate to what's really up there, so the question is, do images like this do a disservice to the general public and astrophotography? While false color images like this are both scientifically valuable and beautiful, they do set up erroneous expectations among the general public, which, as a rule, doesn't understand the process of astrophotography. And even among many persons who take up astrophotography, I think they also set up wrongful expectations. When people are new to astrophotography and they are just starting, they're often expecting to get colors that are something like this. But if one were to look at an image of the Eagle Nebula wherein lies the pillars of creation through a telescope, one would get an image that looks like this. The pillars of creation are toward the center, hazy and pale, and surrounded by a bit of amorphous, cloud-like and paler nebulosity. Now we would see this image through a telescope not due to limitations of telescopes or cameras, but due to our own eyes. Our eyes are evolved for the light-rich conditions of Earth. We have a nearby yellow dwarf star that illuminates our world. It provides warmth and the light that powers photosynthesis, which enables all life on Earth, and essentially base every living thing on the planet in light. And we humans, being diurnal or daylight-oriented, we have eyes that are evolved to accommodate that sun. Our eyes have tiny pupils that are not at all adapted to the night sky. Sure, we can see stars and some of the brighter deep sky structure, such as the galactic arm of the Milky Way or the Great Orion Nebula, but only barely, faintly, in low-light conditions. Our eyes have pupils that may only dilate to 7 to 8 millimeters in diameter, as opposed to my telescope, for example, which has a diameter of 203 millimeters, allowing it to capture almost 1,000 times more light per unit of time than my eyes can. So, when I look up at the sky, I can't see the Star Queen Nebula at all. But if I look at it through a telescope, I can perhaps see this. And this is a far cry from what the NASA images portray. But the biggest problem with the human eye is the human eye does not bank up light over time. To do that, we need to attach a camera to the telescope. With the camera attached, we could run a very long exposure, which will simply collect more and more photons, illuminating the Eagle Nebula more and more as time goes by, like this. As exposure time is increased, the view of the Eagle Nebula will become brighter and clearer. However, there are numerous technical problems with shooting a single long exposure that are beyond the scope of this video. Rather than shooting one very long exposure, modern astronomers and astrophotographers shoot many short exposures. These exposures are all then added or averaged together in a stacking software application. Each exposure adds a little bit more and a little bit different information. So, lots of photographs all added together through stacking can create a single, bright and clear image of an object. I shot the Eagle Nebula for 4 consecutive dark nights, stacked the information together, and transformed the information into this. This is the power of prolonged light collection with a telescope and camera combination. One can bank up more and more light, and light equals information, ultimately revealing more and more of the structure and color of any deep sky object. Now, this is a basic image. I simply added together all the light or luminance and all the color information, the R, G, and B or red, green, and blue channels. No further editing has been done to the image. And if one were to say they wanted to see what the pillars of creation would actually look like as closely as possible to the true colors, this would be it. Let's go ahead and zoom in to the pillars of creation. Well, I think this is a remarkable technical achievement for such a small and inexpensive telescope, a mere Celestron C8 or 203mm aperture telescope mounted on a Skywatcher EQ6R mount here on Earth. It is nonetheless a far cry from the Hubble image here. Bear in mind, neither image is fake. The Hubble image attains its precision of detail because it's in orbit over Earth, where the atmosphere does not blur the information. It also has a huge mirror, allowing it to capture much finer detail. But the colors within the Hubble image are false, and outside the scientific community, that unfortunately creates erroneous expectations about what deep sky objects really look like. Let me carry this illustration further. There is a lot that I can do to enhance and refine the detail captured in my image. I can separate the high and low frequency information. The high frequency information is where the detail is, and sharpen that information. And I can balance the luminosity value of the low frequency information so that light and shadow within the information shows up more clearly. This gives a final result that looks like this. The detail within my information is greatly improved. It's still nowhere near the Hubble, but it is greatly improved. But one thing that stands out in striking contrast is the difference in color. And that is because I shot my image in true color, luminance, and red, green, and blue. Red, green, and blue captures the color information best, and the luminance captures additional luminosity or light and shadow information to very efficiently add more information to the image, thereby reducing noise and improving the quality of the fine detail within the image. Nonetheless, if what I was expecting was the extraordinary colors within the Hubble image, I will not get them. And it's not because the Hubble image is a fake image, but rather false colors have been assigned to the sulfur, hydrogen, and oxygen information to help them stand out better. Hydrogen, which actually shows up as red, a red almost exactly the same as sulfur, has been assigned to the color green, allowing the hydrogen and the sulfur to stand out as very distinct from one another, improving the appearance of structure and detail within the pillars of creation on the right. Unfortunately, the use of false color, it not only encourages the general public and persons new to astrophotography to think the sky looks like false color, but it even inclines many experienced astrophotographers to think their images ought to be developed with false color. And it encourages such cults as the Flat Earth movement, who think that space is fake and Earth is a flat plane. A concept even the ancient Greeks rejected thousands of years ago, but it encourages them to just presume that these images are fake. Now, I'm not saying at all that we should accommodate people like that. Those persons are going to find anything fake. I mean, if you put them all in a rocket and launched the rocket into orbit and gave them a guided tour of the cosmos, when they got back to the ground, they would just be convinced that you drugged them or the windows were demon-possessed or some such nonsense, and they would still say it's all fake. They need to believe that. They cling to ancient myths like security blankets and are afraid of reality. Fundamentally, it's denial of fact at all costs. But for everybody else, such as the general public, they just don't know what space really looks like. And so they may expect the false color look in space. And I've talked to many astrophotographers who, when they were brand new in the art and the science of astrophotography, they too were disappointed with their own works because they did not look like false color images. Let me be clear, neither NASA, nor ESA, nor the Hubble team, nor the JWST team, nor any professional astronomers, nor astrophotographers anywhere ever meant to set up a false set of expectations. They simply have applied the advantages of false color to shooting their images in order to best reveal the information. Nonetheless, the use of false color creates erroneous expectations, and I think something else, and it's ultimately what my video is about. I think it inclines us to fail to appreciate at times the natural beauty of what is really there. Let me show you what I mean. Let me get the Hubble image out of here. And let's restore this image to the true magnification or focal length of my telescope. And now, let's enhance the true color of this image. There is a lot of blue information right around the pillars of creation toward the center, so we'll enhance it by slightly increasing the brightness and the intensity of blue and also the green, which will give the blue a really gorgeous, standout, cyan kind of appearance. We'll also slightly intensify the red saturation so that the red regions will show up better, and then increase the micro contrast, which will enhance the visual definition between very small, almost microscopically small, areas where light changes, which helps to enhance the appearance of detail within the image. None of this is additive. It doesn't put anything fake into the image. It rather simply builds on what is really there, not using false color, but true color and true detail to make the image stand out. This is not a narrowband image. Rather, the true colors of the image have simply been selectively enhanced, capturing and revealing much of the detail that could be revealed by false color, and creating a true color palette, which, while it shows colors as more intense than one might see them were one to look through a telescope, if one were to gather more and more and more information through a camera, this is closer to what one would see. There has been one manipulated difference though. The effect of the green channel has been reduced in the red regions, which allows for the intensification of the red color, and it has been enhanced in the blue regions, helping for the intensification of the blue color. And this helps the hydrogen and the oxygen areas of the image really stand out from one another. So what I'm ultimately saying in presenting you this image is, we don't strictly need false colors to get beautiful renditions of the cosmos. People often remark when they see the images in the Sky Story Astrobin that the color palette is not something that they're used to seeing. Sometimes they wonder how I made it, and I have to explain to them this is just the true colors of the image, just slightly enhanced. And I think sometimes they find that stunning, because it is becoming unusual to see deep sky objects shot in true color. For me, almost without exception, the edits that I do happen to make to an image's color are simply to enhance what's already naturally there. I rarely ever, in fact almost never, turn to false color. When I do add narrowband information to an image, I tend to like to stick to its true colors as well. I'm not saying that I would not make exceptions. For example, if an image had a lot of hydrogen and a lot of sulfur in it, and the only way to bring out the detail between the two was to apply a false color to one of those elements, I certainly would, but I will also avoid doing so if at all possible, and I find almost always it's possible. Usually by simply adding to or decreasing from the moderating color channel, which is almost always the green channel, and refining the microcontrast, the different information within an image can be sufficiently enhanced to really make both color and structure within an image stand out, without having to resort to false color. Ultimately, what I'm saying is that perhaps the biggest disservice created by the usage of false color palettes that have been so popularized by the Hubble, by the JWST, by in fact many professional astronomers and many astrophotographers, is that it may incline us to overlook the natural beauty within our images, contained within their true colors. And that's truly unfortunate, because the true appearance of deep sky objects is, almost without exception, extraordinarily beautiful. And I think it's a shame that we feel false color palettes are necessary to portray them. Granted, what I am saying would not apply if one were developing for scientific purposes. And as previously noted, there are times that it may be beneficial to apply something of a false color palette. For example, if a DSO has a tremendous amount of sulfur and hydrogen mixed together, and it would be better to delineate them. But imagine astrophotography where the true colors, or at least as close as imaging allows us to get to them, were the standard of representation. New astrophotographers would go into the field understanding what to expect. Experienced astrophotographers could appreciate their images for what they were and the colors they were, and the general public would have a truer idea of what is actually overhead, giving less traction to groups like flat earth cults, and, I like to think, more impetus to those persons who truly want to understand, know, and study the cosmos. So you can probably tell with this video that, personally, I hope to see a move away from reliance on these false color palettes. Sure, they're lovely, but they're just not real. And so, when just intending to shoot a beautiful image of the cosmos, I always ask myself, why use a false palette at all when there is so much true beauty up there, out there, just waiting to be discovered? To illustrate my point, here are 7 other images that I shot just this year, all using LRGB as close as possible to a true color palette. I'm sure persons are going to have some thoughts and opinions on this video. Please feel free to leave them in the comments section below. And thanks for watching. And ultimately, whatever approach you take to doing astrophotography, create something wonderful, something beautiful, something that's yours. Learn from it, share it, and have a blast getting out there and shooting the sky.